keep going, keep going, keep going, and stop. Perfect.
Hey Will, what's going on here?
Oh, hi Dr Suze. Well, I've been reading about things called elements, and I wanted to learn more about all of them, so I bought a sample of each one for me to test.
You mean all 118 of them?
Yeah, I can't wait to get started.
Well, if you want to learn about the properties of each element, you don't have to look at every single one. Scientists have been doing that for more than 150 years and have even grouped all the elements together into something called the periodic table.
Oh wow, that's much easier.
Alright mate, that's all the crates, 118 elements, that'll be £55 trillion, please.
Right. Yeah, sure. 55 trillion. This is Dr Suze. She deals with all of that stuff.
What?
I'll get started in the lab.
Will.
Thank you for sorting all of this out. So I read that an element is a substance that contains only one type of atom. But what exactly is an atom?
Atoms are the tiny building blocks of our universe. They're made up of 3 different particles: protons, neutrons, and electrons. Protons and neutrons live in the centre, or the nucleus, of the atom, and electrons orbit around the nucleus along paths called shells. The number of protons in an atom's nucleus is known as its atomic number, which tells us what element the atom is. Most of the time, the number of electrons orbiting an atom's nucleus will be the same as the number of protons, and the number of neutrons in an atom affects how heavy the atom is.
Okay, so an atom is made up of protons, neutrons, and electrons, and it's the amount of protons that tells us what element the atom is.
Exactly. Let's start with the simplest element of them all. This is hydrogen, or H. It only has 1 proton in its nucleus, which means it has an atomic number of 1. It's got a single electron shell surrounding the nucleus with only 1 electron on it, but it's actually the only element that doesn't have any neutrons. We could draw every element's atomic structure like this, but it'd start to get very confusing as we start to look at more complicated elements. So instead, let's take the name of the element, hydrogen, its symbol, H, and its atomic number 1, and rearrange them into a square, like this.
That's much simpler.
If we take all the 118 elements and represent them as these simple squares with a name, symbol, and atomic number, we can arrange them into a grid and create the periodic table of elements.
Wow, it's kind of beautiful.
It really is, but it's not just a pretty pattern. There's a wonderful logic behind that strange shape. We can think of the periodic table as a grid, with rows called periods, which is where the periodic table gets its name, and columns called groups. There are 7 periods and 18 groups. Elements in the same period and elements in the same group all share similar properties.
That's so cool. Hang on, what about that long strip in the middle after group 2?
Well, these are 2 very special groups of elements called the lanthanides and actinides that don't quite fit into any of the other groups. They're a bit different to the other elements, but they're all very similar to each other. For that reason, this strip is usually moved down here and is represented by a square for the lanthanides and a square for the actinides. It also helps to make the periodic table a bit tidier.
Okay, I get it now. So how do we know where each element belongs in the periodic table?
Well, each element fits into a period and a group based on its atomic structure.
So that's the protons, neutrons, and electrons, right?
Exactly, although it's only really the electrons we're interested in at the moment. Let's take a look at hydrogen's atomic structure again. We can see which period row an element belongs in by seeing how many electron shells an atom has. You'll notice that an atom of hydrogen only has 1 electron shell surrounding the nucleus. This means that it belongs in period 1 of the periodic table, which is the top row. We can see which group column an element belongs in by seeing how empty or full its electron shells are. You'll notice that an atom of hydrogen only has 1 electron on its shell, and because an electron shell can't have 0 electrons on it, that means it's as empty as it can be. This means it belongs in group 1 of the periodic table, so let's place it in the top left corner.
Okay, so the period row that an element belongs in is based on how many electron shells it has, and the group column it belongs in is based on how empty or full its electron shells are.
Yep, that's right. Let's look at the next element, helium. You'll notice that an atom of helium has only got one electron shell surrounding the nucleus, which means it also belongs in period 1. However, it's got 2 electrons on its shell. Because this first electron shell can't have any more than 2 electrons on it, it's as full as it can be.
So I reckon that means it belongs in group 18, all the way on the other side.
Yes, exactly. So we'll put it in the top right corner. Let's carry on building the table by looking at element number 3, lithium. If we take a look at its atomic structure, you'll notice that because the first electron shell is completely full, it needs a second shell to add any more electrons. Because it now has 2 electron shells surrounding the nucleus, that means it belongs in period 2, which is the second row. Like hydrogen, a lithium atom has only got 1 electron on its outer shell, so it's as empty as it can be. That means it belongs in group 1.
Okay, so we can pop lithium into the periodic table directly under hydrogen.
Yes, we can, and we can use the same sort of system to find out where all the other 115 elements belong in the periodic table as well.
Ah, I get it now. That's awesome.
Let's play a game. I'm going to show you the atomic structure of an element, and I want you to work out which of the 3 elements it is. Here's the first one. If you want, you can pause the video and do it all by yourself, or keep watching to hear Will's answers.
Okay, so this atom has 10 electrons, and I now know that means it also has 10 protons. The number of protons in an atom is the number in the top corner, so that means this atom is neon.
Amazing! Here's the next one.
Okay, so this atom has 45 electrons, which means it also has 45 protons. The element with the number 45 in the top corner is rhodium.
Wonderful. Here's the last one.
Okay, so this atom has, blimey, 99 electrons and protons, which means that this is an atom of Einsteinium.
Excellent. You're starting to get the hang of this.
So earlier you said that elements in the same period or group all share similar properties. What sorts of properties do they share?
Well, let's start by looking at the periods. As we saw earlier, the period number that an element belongs in tells us how many electron shells an atom of that element has. So, for example, hydrogen is in period 1 because it has 1 electron shell. Silicon is in period 3 because it has 3 electron shells, and tennessine is in period 7 because it has 7 electron shells. Interestingly, although palladium has 4 electron shells, it actually belongs in period 5. It's the only element that doesn't follow the period rule.
Aw, poor palladium, all by itself. So what sorts of properties do elements in the same group share?
Well, elements on the left-hand side of the table are very metallic and become less metallic as you go towards the right-hand side. Can you remember what else happens when you go across the group columns?
Atoms get more filled with electrons, right?
Exactly. Let's take a look at group 1, the alkali metals. That's lithium, sodium, potassium, rubidium, cesium, and francium.
Hang on, what about hydrogen?
Well, hydrogen isn't an alkali metal, but a non-metal. It technically belongs to group 1, but it has very different chemical properties than all the other group 1 elements, so let's ignore it for now. If we take a look at the atoms in group 1, you'll notice that they all have only 1 electron in their outer shell. This makes their atomic bonding very weak, causing alkali metals to be very soft and have low melting and boiling points. On the other side of the periodic table, we have group 17, the halogens. You'll notice that this time they all have 1 electron missing from their outer shell. This makes them very reactive. They want to react with lots of other elements to fill that 1 empty electron space. However, that makes them a perfect match for the group 1 elements, who can fill that space with the 1 electron on their outer shell.
I think I've heard of one of those compounds already. Sodium can react with chlorine to become sodium chloride, right?
Exactly, which is table salt. In fact, nearly all the alkali metals can react with nearly all the halogens to create a different type of salt. Did you know that the name halogen even translates from Greek to I create salt?
That's brilliant.
There are some other groups who also have names that describe how they react with other elements. Group 16 are known as the chalcogens, or I create ores. Group 15 are known as the pnictogens, or I create choking, because of the effects of nitrogen gas. Group 14 are known as the crystallogens, or I create crystals. And Group 13 are sometimes called the icosagens, as they can bond with elements to create a shape called an icosahedron.
Amazing. What about Group 18 at the end? Do they react with anything?
Well, because the outer shells of their atoms are full, they're very unreactive. For this reason, they're known as the noble gases, because it was considered a very noble trait to avoid reacting when provoked. In fact, they're so unreactive that many of the early periodic tables didn't even include the noble gases.
Alright, this layout is so helpful.
Yeah, it is. Although the patterns in the group columns aren't as consistent as the patterns in the period rows, there's still a really useful way of knowing which elements have similar properties to each other.
So each element has a name and a symbol. For example, hydrogen is H, boron is B, and calcium is Ca. But it looks like some of them don't match at all. Why is potassium's symbol K, or gold's symbol Au?
Well, they're not just all random letters. The symbols for elements like potassium and gold come from the names of those elements in Latin. So K stands for kalium, which is the Latin word for potassium, and Au stands for aurum, which is the Latin word for gold. Here are the 10 elements that have symbols representing their names in Latin.
So in Latin, sodium is natrium, potassium is kalium, iron is ferrum, copper is cuprum, silver is argentum, tin is stannum, antimony is stebium, gold is aurum, mercury is hydrargyrum, and lead is plumbum.
Did you know that plumbum is where the words plumbing and plumber come from? Water pipes used to be made out of lead, and so plumbers were people who worked with plumbum, or lead.
Wow, I never realised. Hang on, you've missed one. Why is W the symbol for tungsten?
Ah yes, well, tungsten is very special because it's the only element in the whole periodic table whose symbol isn't based on either its English or Latin name. W actually stands for Wolfram, which is the German word for tungsten.
Das ist sehr interessant. The periodic table is such a wonderful idea. Who's the brilliant mind that decided to arrange all the elements like that?
Well, like a lot of important scientific discoveries, it wasn't just one person that's responsible for the periodic table. Believe it or not, it can actually be traced back to over 2,000 years ago. To show you that, let's use the Timescope. Our journey begins in ancient Greece around 450 BCE. At this point, some of the elements we know today, such as carbon, mercury, and gold, had long been known about, but they weren't considered elements yet. A philosopher called Empedocles is thought to be the first person to suggest that all matter is made of a combination of 4 roots: fire, air, water, and earth. Just like elements today, each of these 4 roots had their own symbol. About 100 years later, another Greek philosopher called Aristotle expanded on this idea, and it was around this time that the 4 roots started to be called elements. It was also the first time that these elements could be arranged into a diagram together.
Oh yeah, it's not quite the periodic table, but I like it.
The properties of these 4 elements were described too. So fire was hot and dry, earth was dry and cold, water was cold and wet, and air was wet and hot. Interestingly, there were similar ideas of the elements in other countries like India and China.
Okay, what happened next?
If we skip forward to 1520 CE, we can find a new idea called the 3 primes, created by the Swiss alchemist Paracelsus.
What's an alchemist?
An alchemist was someone who practiced something called alchemy, which was like an early version of chemistry. Like in ancient Greece, we can see the 4 elements: earth, water, air, and fire. But now we also see that these elements were believed to combine to form salt, mercury and sulfur, although they weren't the same as the salt, mercury and sulfur we're familiar with today. If we move forward to 1718, we come to this table.
Ooh, that looks interesting.
This is the Table of Affinities by a French chemist called Étienne François Geoffroy, which not only lists supposed elements, but also arranged them into a table based on how they chemically react.
Hey, that's like the periodic table.
Exactly, we're starting to get closer now. In 1789, another French chemist called Antoine Lavoisier compiled a list of elements. This time there's only 2 elements on there that we now know are wrong, light and heat. All the others are correct. In 1808, an English chemist called John Dalton created a table that not only listed all correct elements, but also added a brand new piece of information.
Oh, I see it. Those numbers on the right. What are they?
They're all the atomic weights, which is how elements were measured before people knew anything about protons, neutrons and electrons. We'll come back to atomic weights in a moment. In 1829, a German chemist called Johann Wolfgang Dobereiner noticed a pattern. He saw that various groups of 3 elements had similar properties. He called these groups triads, and they were things like lithium, sodium and potassium, calcium, strontium and barium, and chlorine, bromine and iodine. He then realised that there was a pattern with their atomic weights as well. If you took the average weight of the smallest and largest elements in a triad, it'd be very close to the weight of the element in the middle. For the next few decades, people tried to arrange the elements into lots of different tables and diagrams. There's this triangle by Leopold Gmelin from 1843, this table by Julius Lothar Meyer, and this one by William Odling from 1864, this spiral by Gustavus Detlev Hinrichs from 1867, and even this cylindrical screw by Alexandre-Émile Bégouillet de Champcotois from 1862.
These all look brilliant. Hold on, looks like you missed one. What's that table?
This one is by John Newlands in 1865, and just like how Dobereiner noticed repeating patterns of 3 or triads, Newlands noticed repeating patterns of 8 or octaves.
So it sounds like chemists are starting to notice that the properties of elements have repeating patterns.
Absolutely, and this is where the periodic table we know and love starts to take shape.
Hang on, why are we looking at a train station?
I'm just looking for our last piece of the puzzle. No. Here we go. This is the Russian chemist Dmitry Mendeleev.
Who's playing solitaire by the looks of it.
Not quite. Let's look a bit closer.
Oh, they're not playing cards. Those are all the elements.
Yes, they are. Just like Dobereiner and Newlands before him, Mendeleev noticed repeating patterns in the elements like their atomic weight and chemical properties. It's said that to try and figure out what was going on, Mendeleev would play a card game where he'd try and arrange the 63 then known elements into the correct layout.
Huh, what a great idea. Although it looks like he's struggling a bit.
Despite playing for hours at a time, he actually couldn't find a layout that worked for those 63 elements. But this is where he had a bright idea. Maybe there's some elements missing. With this in mind, he was finally able to create a periodic table that seemed to work. Not only that, but you'll see that this one includes 4 elements that hadn't been discovered yet, and even predicted their atomic weights.
That's incredible, but this still doesn't quite look like the modern periodic table.
Well, this one from 1869 is only the first of Mendeleev's tables. These 2 from 1870 and 1871 will start to look a lot more familiar. Let's take a closer look at this table from 1870. You'll probably recognise some elements like calcium, zinc and titanium. But in the middle of those, Mendeleev left gaps to show elements that he thought existed but just hadn't been discovered yet. So we have Eka-Boron, Eka-Aluminium and Eka-Silicon. The amazing thing is that around 5 years later, French chemist Paul-Émile Lecoq de Beaubaudran discovered Eka-Aluminium. It became known as gallium and matched Mendeleev's prediction very closely.
How amazing! Was he also right about those other elements he predicted?
Absolutely! Eka-Boron was discovered in 1979 and named Scandium, and Eka-Silicon was discovered in 1886 and named Germanium. Mendeleev later predicted one more element, which he called Eka-Manganese, which was discovered in 1937 and named technetium. That's 62 years after his prediction.
Wow! I never imagined that one table could have such an interesting history with so many people involved. Okay, I'm going to quickly remind myself. The periodic table organises all elements into 7 rows called periods and 18 columns called groups.
Or 32 columns if you're looking at the full table.
Right. As elements go down the period rows, their atoms have more electron shells, and as the elements go across the group columns, those shells become more full with electrons, making elements in the same group have similar properties.
Yep, you've really got the hang of it now, Will.
Ah, amazing. There's just one more thing. Over time, the periodic table has been getting filled in more and more as people have been continually discovering new elements. Does that mean that it's now fully complete?
The really exciting thing is, we don't know. The current periodic table could just be a tiny section of a much larger and maybe even infinite table of elements. Although most of the elements occur naturally on Earth, the last 24 elements had to be synthesized or created in laboratories. As elements become heavier, they become much more difficult to synthesize, but that doesn't mean it's impossible that more could be created.
Oh wow! So there may never be a final element that makes the table complete.
Well, many scientists believe that there probably is a limit to how heavy an element can be without being too unstable to be synthesized. There's a theory that element number 126 may be the last element stable enough to exist, but right now we just don't know. The periodic table could go on forever and ever and ever.
That's so incredible. I'll have to keep my eye out for element 119. Thanks, Dr. Suze. If you want to keep practicing, download the worksheet in the video description. Make sure to check out the bonus video where Dr. Suze and I give you a fact file on every single element, all 118 of them. If you like this video, make sure to give it a thumbs up. Subscribe to learn more science, English and maths with Will, and let me know what you want to learn next by commenting below or emailing info@learnwithwill.co.uk.